All right, so let's take a look at simple harmonic motion. Now, normally in AP Physics 1, we cover rotation first, but I think harmonic motion is closely tied to energy, that I like to cover that before we do the rotation topics. So let's just remember that simple harmonic motion is an oscillating motion that is a restoring force. This is the key thing that defines that. In general, there must be a restoring force that is proportional to the displacement from the equilibrium. So it's not just enough that it has a restoring force, it must be proportional to how far we are from the equilibrium position. That's the general way that we handle harmonic motions. Now from that definition, so a lot of people get confused. This is the definition here. And then there are properties that come about because of that. There are some characteristics. One is that the motion is periodic and that the position, velocity, and acceleration are sinusoidal curves given by, this is the position curve, but the velocity curve is going to look very similar, and we'll talk about how that operates. The total energy, assuming you include the correct objects in the system, remains constant throughout, so energy is conserved. Again, whether or not we use the pendulum versus the mass springs or things like that, that's going to be the total energy is overall going to be the same. And we cover two types, the pendulum and mass on spring. Now, with this change into 2025, I think there's going to be a bit more emphasis on this graph. This equation was given in past exams, but not really used very much. So I want to make sure we understand exactly what this equation looks like. So I'm going to pull up like a Desmos example of what this thing kind of looks like. Let me shrink this back. And let's zoom in over here. So this is a sine, and let's talk about omega is 0. Not omega 0, sorry. The phase shift is 0. Let's talk about all of these things. So in general, A is the amplitude. So that's going to be the peak value that you're going to hit. It's 1. It can shrink up and down. Changing the A value here is going to change that amplitude. That is the furthest this displacement. But notice changing the amplitude has no effect on the period. The period is effect. This is a review from your pre-calculus when you did this. The omega, the thing in here, actually dictates the period. And if you guys remember, it's been a while since you did pre-calculus, or maybe you guys are doing concurrently. If you remember, when you plot graphs of sine and cosine, the period is given by 2 pi over omega, or that omega is 2 pi over the period. Either way is fine. You want to think about it. But this is called the angular frequency. It is in radians per second. This is the first time we are really focusing on radians in AP Physics 1. And so the omega here dictates what the period is going to look like. It's going to shrink the period, the time it takes to repeat. And then the phase shift is really just a horizontal shift. It just kind of tells you where you're starting. So usually we don't mess too much with the phase shift other than just where the starting point is. But you'll see it's just going to move it left and right as we adjust that phase shift. So that's just saying, where does time 0 begin in the motion? So that one we don't really worry too much about. But the omega affects the period, and then the amplitude is just sort of where we start and where we end there. Okay, so let's take a look at each of the examples. So we look at pendulums. Pendulums have a period equation. They always have a period equation. In AP Physics C, you have to derive this, but in AP Physics 1, you just need to know it's 2 pi L over G. It's only affecting, and this is the thing about pendulums. It's a ball that's swinging, and it's a simple harmonic motion only for small angles, about less than 15 degrees approximately, but it's just like more accurate. The further away, the bigger the angle, the less that it looks like a simple harmonic motion. The pendulum period only depends on the length of the string and the acceleration due to gravity. It is not affected by the mass of this thing. So there might be a mass of this bob that's swinging. That does not affect the period, actually. At maximum height, here there's no kinetic energy. That's always true in general, like when you're exchanging between gravitational potential and kinetic energy. So as it goes up, it loses kinetic energy and gains gravitational potential energy relative to this height here. And this is a little bit of illustration on how the heights can be based off of the length of the rope and the angle. If you want to see that, the maximum height is going to be L minus L cosine theta there. At maximum height, there's no kinetic energy. All of it is gravitational potential energy. And if you go down here at the equilibrium position, right down here, it has the maximum kinetic energy and thus moving the fastest. And if you set this where h equals 0, then it has no gravitational potential energy either. So it's an exchange between gravitational potential and kinetic energy. One thing to note about this is the net force at the equilibrium position for a pendulum is not 0. There's no horizontal forces, but there is a vertical force because there is a centripetal acceleration directed towards the center of the circle. So be very careful about that when they're swinging. A lot of the times for the mass springs, we say the net force is 0 at equilibrium. Here, the net horizontal force is 0 at the equilibrium position at the lowest point. But the net force itself is not zero. In fact, the tension will be greater than mg due to the fact that it's moving in a curved path or a circular motion, just like we talked about in the Unit 2 review, forces review. Horizontal mass spring, the period equation is given by this. The period only depends on the mass and the spring. So this is a horizontal mass spring. This is where we're oscillating horizontally like this. And here I illustrate the spring force is the one that is operating the proportional force, because remember the spring force is equal to kx, and that is proportional to how far we stretch it. When the spring is relaxed is when the spring force is zero, and that's where the net horizontal force is zero. So this is the equilibrium position. At the furthest extremes are the amplitudes where you're moving to the right and to the left, okay, illustrating that motion. So the amplitude is at the maximum stretch or maximum compression of the spring, but it is the same on both sides there. Again, at the maximum compression or the stretch, a couple of things are true. The velocities are zero here. So that means it has no kinetic energy. It has the most spring potential energy. So in this one, we're exchanging spring potential energy to kinetic energy. So we have maximum spring potential energy here and here, but no kinetic energy. At this part here, because the spring is at its relaxed length, we have maximum kinetic energy and no spring potential energy. So here has max kinetic energy and thus max speed and no spring potential energy. Whereas here it's the maximum. The forces is greatest when we are furthest from equilibrium. Okay. Vertical mass spring is probably the most complicated one. The period is still given by the same equation, 2 pi root m over k, and that you might wonder why that is. That just has to do with how the differential equation is set up and how it's solved, which is beyond the scope of this class. Suffice to say, the period will still be the same, even though it's vertical, even if it's at an angle on a ramp. As long as there's no friction, it would be the exact same thing as well. Now, this one, you're exchanging between three forms of energy because there's the spring, there's a change in height, so there's gravitational potential energy, and then there's kinetic energy. So it's a little bit trickier to talk about something like that. The amplitude is where we're going to have the max potential energy and no kinetic energy, because at the maximum stretch or compression, the velocity is zero, so no kinetic energy at those points. Here, it's going up and down. It could be hung. This one's a compressed, but it could be hung from the ceiling. Either way, it doesn't really matter. But the key thing you have to recognize is that here the net force is zero at the equilibrium position, so it has the max kinetic energy. However, there's still some spring potential energy because here at the equilibrium position, the spring force equals the gravitational force. So that means the spring is compressed or stretched a bit at the equilibrium position, unlike this one here. So the thing that's similar between the two is the net force is zero at the equilibrium position here, but that doesn't mean the spring force is zero. It means the gravity and the spring force balance each other out, so the net force is zero. And then at these points, you can see when it's fully compressed down here, the spring force is maximum. Here, gravity and spring force are pointing down, and it's not necessarily the same amount. So this and the forms of potential energy also vary because down here we have the least gravitational potential energy. Here we have the greatest gravitational potential energy. But so the spring potential energy might be different between these two. Will definitely be different because the total potential energy is the same at the endpoints there. It's just the mix of how much is spring potential and how much is gravitational potential is going to vary because of you see the different heights there, and thus the springs are not going to be exactly compressed the same. At the equilibrium position, we have max kinetic energy. We still have some potential energy because there's going to be some gravitational potential, and because there's a spring force means the spring has to be stretched or compressed a little bit in order for that to occur. Okay, and so what the main things that we really focus on is understanding that sinusoidal behavior, understanding the period, and primarily using conservation of energy in our analysis. So let's go through a few questions here and kind of see how this works. So in a trial of experiment 1, block 1 of mass m is oscillating at the end. So this is a horizontal mass spring. Friction between the floors negligible. Block 1 oscillates with an amplitude d, 0. Okay, how do the maximum speeds and maximum kinetic energies of the two trial is attached to block 1 and oscillates with amplitude d0? How do the maximum speeds, maximum kinetic energies? Okay, so let's first talk about the maximum kinetic energies. So remember, at this stretched point, okay, we have only spring potential energy here, right? So that's 1/2 k x squared, and that's 1/2 k, and then that is d0 squared. So this is our maximum stretch. And then here we're going to have the maximum kinetic energy, right? So notice that we have the same spring potential here and here because the spring potential is just based on how much we've stretched it. So once we release it, all of that energy, the spring potential energy here is 0. It all gets converted to kinetic energy. So the kinetic energy is going to be 1/2 k d0 squared. And here it's going to be 1/2 k d0 squared. Because they have the same spring potential energy, which is the maximum energy. Remember, the total energy is conserved for the block and spring system. So they're actually going to have the same maximum kinetic energy. So it is going to be the same in both trials. Now, what is that kinetic energy? Well, that kinetic energy does equal 1/2 mv squared for trial 1. And for trial 2, it's going to be 1/2 2m v squared. Okay, so this is V1, this is V2. So say at this point, he's moving at V1. This point, they're moving at V2. So they have the same kinetic energy in the system overall. However, this has more mass, so he's got to be moving slower if these two are the same. So they have the same kinetic energy, but because this guy has more mass, a lot more of that kinetic energy should do is more massive. So he's not going to be moving quite as fast down here. So it's going to be equal in both trials. Oh, sorry. I mixed up. The maximum kinetic energy would be equal in both trials, but the maximum speed is going to be greater in trial 1. So it's going to be B here. So that's where we're using that energy. You might think like, well, Alan, how come the 1/2 mv squared, it's twice the mass, but you don't know what the speeds are. So you can't compare those necessarily. You're assuming they're moving the same speed, but you don't know they're moving at the same speed. The only thing that's easy to compare is that at the maximum stretch, right, we're stretching the same amount, same spring constant, so it has the same spring potential energy, and that gets converted to kinetic energy. So that's what's similar between the two. And therefore, we can translate to what the kinetic energy is going to be doing. Again, that's that conversion of energy that's happening between spring potential and kinetic energy. All right, two systems, simple pendulum, mass hanging out, ideal spring, both have a period of 1 second. So the period of a pendulum, remember, is 2 pi root L over G, because they're already asking about the period. The period here is 2 pi root M over K, and they're saying this is equal to 1 in both of these. They are then set to a small oscillatory motion on planet X, which is the same diameter Earth, but twice the mass. So this is relating a little bit to what's going to happen here. Which of the following statement is true about the periods of the two objects on planet X compared to their periods on Earth? Well, here, the period is only dependent on the mass of the object, not the weight of the object, the mass of the object and the spring constant. We have not changed that. So this one is going to stay the same, no change when we move to a different planet. However, this one is going to have a different G. The length of the pendulum is the same because we haven't physically changed the pendulum. We're only changing the planet. And remember that G, that gravitational field, is Gm over mass of the planet over radius of the planet squared. And they're saying it has same diameter, so same radius, but twice the mass. So this is G times 2 times the mass of the Earth over the radius of the Earth squared. It says 2gme over radius of the Earth squared. So basically it says twice the mass, so it's going to have twice the amount of, so it's going to be 2 times 9.8 or 2 times 10. Okay, so we're going to increase the G. So the G is going to go up. So this guy goes up. It's on the denominator. When you have a bigger denominator, overall the number has to shrink. So the period is going to go down. So then the pendulum, the period of the pendulum is shorter. It's going to decrease, right? The pendulum goes down. And the period of the mass of the spring is the same. No change there. So let's take a look at an FRQ problem here. So we have a block of mass M1 is sitting at rest on top of a vertical spring with the spring constant K in equilibrium position. The block is pushed down a distance A and released, and the block oscillates up and down. Suppose the block is pushed down a distance larger than A below the equilibrium position. Will the maximum kinetic energy during the oscillation increase, decrease, remain the same? So remember, the maximum kinetic energy occurs at the equilibrium position. So if you push it down further, there's that exchange of energy, right? You're going to push it down, you're going to give it more spring potential energy, and that's going to get ultimately converted into more kinetic energy. So it's going to increase, and the reason is going to be is like you will be doing greater compression means more spring potential energy, resulting in a greater maximum kinetic energy at the equilibrium position. That's all you really got to say. There's more energy, right? There's more energy in the system. When I push it down further, there's going to be more energy, so there's going to be more kinetic energy out there. So now we're going to derive an equation for the maximum kinetic energy. So that's the energy here in terms of M1A, K, and fundamental constant. So we want to do conservation of energy. And so our system is going to be, because of the change in height, because of the spring, it's going to be a vertical mass spring. We have our system is going to be the spring plus the Earth plus the object itself. So we're going to look up the energy here versus the energy here. Now, it's always a little bit tricky. The tricky part is the spring is compressed at the equilibrium. So here's the equilibrium position. That's where the maximum kinetic energy occurs. And that occurs where the F net equals 0 because there's no net force. And so one thing that's helpful when you're deriving this is always think about the relaxed length of the spring. So this is the relaxed length of the spring. And in equilibrium, we are compressed some. So there's some spring potential here. There's some gravitational potential energy. And there's some kinetic energy here. And down here, if we make this H equals 0, we only have spring potential energy because there's no gravitational potential energy at this point when the block is down here because the height is 0, and there's no kinetic energy because at the maximum extreme point, the kinetic energy is 0. So the spring potential energy, so the energy at the bottom is going to be just 1/2 kx squared. Now, how much are you compressed? Well, that's the tricky part. This is the relaxed length. We're compressed this distance here. That's not A. It's A plus whatever, like the distance from here to here is A, but the distance from here to here we have to think about. And how much are we compressed at this point is based off of the equilibrium position. Okay, so the equilibrium position, we know the net force has to be 0. So we're going to draw a free body diagram and say like, oh, well, we have M1G and we have Kx here. So this, because at the equilibrium position, the net force is 0, we have M1G is going to equal Kx. So X is M1G over K. So this distance here is M1G over K. So that means how much are we compressed at the bottom here is 1/2 K times M1G over K plus the amplitude. That's how much we've compressed the spring. Okay? Now the energy at the top, at the equilibrium position, we're going to have the kinetic energy. That's what we want to solve for. That's the maximum kinetic energy. We have gravitational potential energy because we're located A above the H equals 0. So that's M1GA. And we're also compressed some. We have some spring potential energy, 1/2 K. And how much are we compressed from the relaxed length at this point is M1G over K squared like that. Okay, so now we want to then set those equal to each other by conservation of energy. Oops. Is equal to the kinetic energy plus M1GA plus 1/2 K M1G over K squared. Now, we want to solve for the kinetic energy down here, right? So the kinetic energy is going to be this guy. Now, one thing that's nice that you can do, and this is why it's not obvious, because you might be like, well, this is kind of a complicated expression. Let's FOIL this thing out, expand this thing out. This is 1/2 K, first term squared, M1G over K squared, plus 2 times this, so 2A M1G over K, plus A squared is going to equal this part here. And if you FOIL out the 1/2 K, you're going to 1/2 K times M1G over K squared, 1/2 K times that, the 1/2 times 2 cancel, K times A, you have KA M1G over K, and then 1/2 KA squared. Now the K's here cancel. And one of the things you should note is if you look at the left side and the right side, is this term and this term match. So you can subtract them. They will cancel on both sides. This is A times M1 times G. This is M1GA. Those are also going to cancel. So you end up on the right side having kinetic energy, and on the left side you have 1/2 KA squared. So the maximum kinetic energy is 1/2 Ka squared. Now you might think like, oh, doesn't that mean the spring is compressed A? Not exactly. That's not how spring potential energy works. But in this scenario, based off of how the oscillation is going to work, that is going to be the kinetic energy. And that's a simplified expression. Even though it was very complex, that's what we derived. Does our equation of part B agree with our reasoning from part A? Well, we said if we increased A, then the kinetic energy will increase, and we have found that to be true. Yes. Increasing A will increase the 1/2 Ka squared, or the kinetic energy, the max kinetic energy. So this is the max kinetic energy we just solved for. Okay. All right, let's look at the next one here. So a simple pendulum of length L and bob mass is hanging from inside a space station orbiting the Earth with radius r. When oscillating a small angle, the period of the pendulum is t. If the pendulum is brought to Earth, how would the period of oscillation change? So here we go, 2 pi root L over g. Now, what's going to happen is when you are further away from the Earth's surface, right, the g is equal to g mass of the planet over r squared. And so what happens is as you bring it closer to the Earth, the g increases. So what's going to happen as you bring it closer to the Earth's surface, this is going to go up. The denominator is going to go up, so the period is going to go down. So you would say it decreases. And why? We would say being closer to the planet, so closer to the planet has a larger gravitational field. And the period is inversely, because on the denominator, proportional to the square root of g, because it's technically not g, but the square root of g in there. Derive expressions for the period of oscillation of the pendulum in orbit in terms of L, R, and fundamental constants. Okay, so we just plug that part into g. So we're going to start with this. T is equal to 2 pi root L over g. That's going to be 2 pi root L over this thing, which is g mass of the planet divided by r squared. This is the mass of the Earth. So this is the mass of the Earth over r squared. And that's equal to 2 pi root L r squared over g mass of the Earth. Now, this might be, this is going to be a little tricky because if you want to get rid of the constant, so technically I think I meant to say mass of the, so let's say you're allowed to use mass of the Earth, orbiting Earth, ME. That's just statement there. So we can leave it like that. Or if you want to put it in terms of g, this is just an extra mathematical step. This is not totally necessary. Is we know g of the 9.8 is equal to g mass of the Earth over the radius of the Earth squared. So you could put it in terms of radius of the Earth instead, because you could say this is g times the radius of the Earth squared. But because what you could do is you could say this is equal to g times mass of the Earth, and you could replace that into there. Not strictly necessary, but like I think in this case it's fine to put in terms of mass of the Earth. I'm going to modify in the notes to include the mass of the Earth as a constant you're allowed to use. Okay, does the equation for the period of the pendulum agree with our reasoning for part A? So what we said was what is going to happen is yes, because as the R decreases, so we're closer to the Earth center, the period will decrease, right? Because on the numerator here, right? So, so get that, and that's it for that.